This time we're looking in more detail at the phase response and at a slight variation on the RC circuit. As we've seen in previous videos, the phase response or the argument of the frequency response for this simple RC circuit is minus the arctangent of omega RC. And if we consider what that evaluates to in the case of very low frequencies and very high frequencies, then we see that at very high frequencies, it's going to be approximately equal to the minus the inverse tangent of infinity, and that's minus 90 degrees. At very low frequencies, it'll be approximately equal to minus the arctangent of 0, and that's just 0 degrees. So we'll get this kind of graph here. It starts at 0 degrees at low frequencies, ends up at high frequencies at minus 90 degrees, and in between moves smoothly from 0 to minus 90 degrees. Now, something interesting happens if you look at what the phase difference is at the break frequency. Remember, we can write the frequency response of this network in terms of the break frequency as 1 over 1 plus j omega over omega b, the break frequency in radians per second. And if I write this in terms of the amplitude response and the phase response, I would get 1 over square root of 1 plus omega over omega b squared times e to the power of j minus the arctangent of omega over omega b. So, at the break frequency, the amplitude response at the break frequency would be 1 over the square root of 1 plus omega b over omega b, since I'm evaluating this when omega equals omega b squared. That's just 1 over the square root of 2. And if I was to work out what that is in terms of dB, it would be 20 times log to the base 10 of 1 over the square root of 2. And if I work that out, the answer comes out to be approximately minus 3. It's actually very close to minus 3. Minus 3.0103. Usually we don't bother about the small difference, and we just call this the minus 3 dB point. And in terms of the phase response, at the break frequency, the phase response would be the minus the arctangent of omega over omega b, but when omega is omega b, that's just minus the arctangent of 1. Well, the angle that has a tangent of 1 is 45 degrees. So this is just minus 45 degrees, which is exactly halfway between the low frequency approximation, that the phase angle is 0 degrees, and the high frequency approximation, that the phase angle is minus 90 degrees. So you've changed by exactly half. Oops, not a very good drawing, sorry. You've changed by exactly half of the total change in the phase from 0 to minus 90 at the break frequency. And these limiting cases and the case at the break frequency are useful things to know. If you have a circuit with this type of frequency response, which could be written in terms of the break frequency in this form here, then low frequencies, the gain is 1 or 0 dBs, and the input and the output are in phase. The phase difference is 0. At very high frequencies, a long way above the break frequency, then the gain is decreasing at 20 dBs per decade, as we've seen. The slope of that straight line on a plot of dBs against the log of frequency was minus 20. And the output is lagging the input by 90 degrees. At the break frequency itself, the gain has dropped by 3 dBs, and phase change between the output and the input is minus 45 degrees. Now, let's have a look at a slight variation on this circuit. Here, I've just swapped the capacitor and the resistor around. It's still a potential divider. I can still use the potential divider equation to work out the frequency response. And the frequency response in this case would be the resistor divided by the resistor plus the capacitor in terms of their complex impedances. Multiply top and bottom by j omega c again, and I would get j omega c times r over 1 plus j omega c times r. So the numerator is different, but the denominator is the same as the expression that we had last time. If we want to work out what the amplitude and the phase response of this frequency response is, then we need to convert this expression into an amplitude response and a phase response. And we can do that by taking the numerator and the denominator and expressing them both in a polar form. Well, omega CR times J on the Argand diagram is going to appear somewhere up there. It's a positive imaginary number. Its magnitude is omega CR. Its phase is always going to be 90 degrees, or pi over 2. So I could write that numerator term there as omega CR times e to the power of j pi over 2 in its polar form. The denominator here is exactly the same denominator as we've seen before. So we could immediately write that as 1 plus omega squared c squared r squared e to the power of j minus the arctangent of omega rc. It's just exactly the same as the case that we've done before. Therefore, we can write the entire frequency response as omega CR over the square root of 1 plus omega squared c squared r squared, that's the amplitude response, times e to the power of j pi over 2 minus arctangent of omega rc. That's my phase response. That's the difference between the output and the input in terms of phase. Let's look at some limiting cases for this one. At very low frequencies, omega is much, much smaller than 1, so we can neglect this term with respect to the 1. You just end up with omega CR times e to the power of j. Well, omega RC is going to be very, very small. The arctangent of a very, very small number is approximately 0. It's just going to be e to the power of j pi over 2. That suggests that the output is leading the input in phase by 90 degrees, pi over 2, and has a magnitude of omega CR times the amplitude of the input. At high frequencies, where omega squared c squared r squared is much, much bigger than 1, I can neglect the 1. That means that I'm just going to get omega CR divided by omega CR, which is just 1. And I'm going to get 1 times e to the power of j pi over 2 minus the arctangent of a very, very large number. Well, the arctangent of a very, very large number is approximately 90 degrees, or pi over 2. So this would just result in pi over 2 minus pi over 2, which is 0. So e to the power of j, 0. The output and the input are in phase. I can think about this low-frequency approximation in terms of the asymptotic behavior of this graph as well. Similar to how I did before, just express this in terms of dBs by taking 20 times the logarithm to the base 10 of both sides. And that would give me, if I just consider the amplitude response there, h of omega modulus, the amplitude response, equals omega CR. So 20 times log 10 of the modulus of h of omega would be 20 times log 10 of this. And again, if I express this in terms of f, frequency in hertz, rather than omega, that would be 2 pi times f times CR. That would give me 20 times log to the base 10 of f plus 20 times log to the base 10 of 2 pi CR. That is a constant. This is a gradient of 20 if I plot the amplitude gain in dBs on my y-axis and the logarithm of the frequency as my x-axis. I would end up with a straight line with a gradient of plus 20. And that's 20 decibels per logarithm of frequency. We usually write that as 20 dBs per decade. Decade because if you move in frequency from 1 Hz to 10 Hz, or 10 Hz to 100 Hz, or 100 Hz to 1 kHz, you're moving through a decade of frequencies, but the logarithm of that frequency has changed by 1. This is what a plot of the phase response would look like. Starts at 90 degrees, moves down to 0. We can have a look at this one in the simulator as well. You can see that at very high frequencies, when we're up here, the output is approximately equal to 1 volt, the same as the input, and the phase of the output is the same as the phase of the input, both 0 degrees. But as I go down to lower frequencies, the phase of the output is approximately 90 degrees ahead of the phase of the input, although the amplitude has dropped considerably. Looking on the phasor plot at a very low frequency, a long way below the break frequency, you can see that the phasor representing the output here has a positive imaginary component, and in fact it's almost entirely positive imaginary. And on the time domain plot, the maximum of the output occurs approximately 90 degrees before the maximum of the input. That's all for this one. Next time, we'll have a look at a slightly more complicated circuit.